Today, we're diving into a new frontier in physics, and it's based on two absolutely groundbreaking papers. We're talking about a world where scientists are literally blurring the lines between light and matter. This is the world of chiral quantum matter. And you know what? It could change everything we think we know about building with light.
Okay, so let's jump right into this with a question that honestly sounds like it's straight out of science fiction.
I mean, really think about this for a sec. What if you could take a particle of light, a photon, and just fuse it with a particle of matter, like an electron? The result wouldn't really be light anymore, and it wouldn't be matter either. It would be this totally unique hybrid particle that plays by a completely new set of quantum rules.
Well, guess what? This isn't just some wild thought experiment. Physicists actually have a name for this bizarre hybrid. They call it a polariton, and this little guy is the first key character in our story today.
So what in the world is it? A polariton is what we call a quasiparticle. Now, don't think of it as a fundamental particle. It's more like a description of a collective behavior. It happens when light and matter get locked into such a tight dance, what physicists call strong coupling, that they start swapping energy back and forth so fast they basically can't be told apart anymore. It's kind of like a ghost, that's the photon, merging with a person, the electron. The result is a whole new thing with properties of both.
Okay, check this slide out. This shows us what's happening on an energy level. So look at that graph. Imagine two lines for the energy of light and matter, just on their own. Normally, they could cross. But when they strongly couple, they just refuse to occupy the same energy level. It's like they repel each other, and they split apart to form two totally new energy paths. And those new paths, those branches, are the polariton states, one with a bit higher energy and one with lower.
But just creating this light-matter hybrid, well, that isn't the whole story, not even close. To unlock its true power, scientists have to be able to control its direction. And this is where our second key concept, chirality, steps onto the stage.
So, what is chirality? In physics, it's basically any situation where the mirror image of a system just doesn't behave like the original. The simplest way to think about it, look at your hands. They're perfect mirror images of each other, right? But you can't lay one perfectly on top of the other, they just don't line up. That handedness is chirality. And this slide right here shows how scientists are actually engineering that handedness into light. What you're looking at is this tiny channel called a waveguide. It's smaller than the wavelength of light itself. And because its structure is so precise, the light waves can only really fit and travel through it in a very specific orientation. What this means is that light that's polarized to spin one way, let's say clockwise, it can travel forward. But light spinning counterclockwise, it gets blocked or even forced to go the other way. It's basically a physical filter for the direction of light's spin.
So what you get is a quantum one-way street. And let me tell you, this is a huge deal. Because in most systems, from a bouncing ball to a beam of light, the path forward is just as good as the path backward. By breaking that symmetry, physicists get this incredible, unprecedented level of control over how light and energy move around at the absolute tiniest scales. Okay, so how is this actually being built in the real world? I mean, this isn't just theory. Researchers are out there actively building these chiral environments, and they're using a stunning variety of experimental platforms to do it. This slide just gives you a little taste of the sheer breadth of all this research. I mean, every one of these images is a different experimental setup. For instance, some of them use these tiny ring resonators that act like little circular racetracks for light. Others, you can see, use these really intricate photonic crystals that guide photons through a maze. And a lot of them use these ultra-thin 2D materials like graphene. They're all different ways of getting to the same goal, creating and controlling these one-way chiral interactions.
And the difference this makes is just profound. In the optics we're used to, light travels symmetrically. The path forward is the same as the path backward. The interactions are reciprocal. But in chiral quantum optics, suddenly the direction depends on the light's spin. This lets you have non-reciprocal or one-way interactions, giving us precision control right down to the level of a single photon.
So, why does all this matter? I mean, this is way more than just a fascinating physics puzzle. Being able to control light and matter in this fundamentally new way, well, it unlocks a whole new toolbox for future technologies. First off, think about quantum computing. Those computers will probably process information using photons. So the ability to perfectly route single photons down these one-way streets without any loss or interference, that is an absolute game changer for building the logic gates, the fundamental guts of these future machines.
So this diagram shows a design for one of these quantum logic gates. In a regular computer chip, your logic gates are transistors, and they manipulate electrons. Well, here, the gate uses these one-way chiral pathways to control how photons interact with each other. It's a fundamental building block for a computer that calculates with light instead of electricity. Pretty cool, huh?
And another really exciting application is in creating completely revolutionary new kinds of lasers. We're talking about lasers that are far more robust and efficient than anything we have today. This here shows a design for what's called a topological laser. The key idea is that the light is forced to travel only along the outer edge of the material, kind of like a car on a one-way circular track. It can't turn around and it can't get scattered by bumps or defects in the middle of the road. This topological protection creates an unbelievably stable and robust laser beam, way more resilient than conventional designs.
And honestly, that is just the beginning. The possibilities here are truly vast. We're talking about creating novel quantum light sources, transferring quantum information with almost perfect fidelity, building ultra-sensitive sensors, and even exploring some of the most exotic physics out there, like completely new many-body phases of light and matter.
And hey, don't just take my word for it. As the researchers themselves state in one of the papers, the opportunities presented by these chiral interfaces are just vast. And they're especially excited about the ability to reveal and study exotic quantum many-body phenomena. You know, the really weird collective behaviors that pop up when lots of quantum particles start interacting. Which brings us to a final, pretty provocative thought. By learning how to fuse light and matter, and then force them down a one-way street, are we witnessing the birth of a whole new technological age, one built not on silicon, but from light itself? It really feels like we are laying the foundation for the next quantum revolution.